Parallel universes have fueled lots of wild musings among science fiction fans. The striking thing now is that increasingly high-powered scientists are pouring their brain power into probing whether the reality of the cosmos is not so much a universe, but really a multiverse. Brian Greene is a theoretical physicist at Columbia University. He is the author of The Elegant Universe, and his new book is The Hidden Reality, Parallel Universes and the Deep Laws of the Cosmos. And Brian Greene joins me in Toronto. Hello.
How are you?
This is mind-bending stuff. It's so complicated, it's no longer complicated.
Well, the wonderful thing about it is that people have, as you have said, thought about the possibility of other universes for a long time. It's sort of a natural idea to think about once you realize that there are many planets and many stars and many galaxies. Maybe there are many universes. But it really has only been recently that our mathematical approaches to understanding the deep laws of the cosmos have suggested this as a real possibility. It's by no means a certainty. It's highly, highly speculative, but we are now taking the idea of many universes far more seriously than we ever did.
And even before you were doing equations, you were musing about this as a kid because you opened your closet door.
Yeah, that's true. I do describe in the book how when I was a little kid, in my room, the closet had a mirror built into the door, and I also happened to have another mirror on a wall nearby, and when the closet door was open, the two mirrors would face each other. And so, of course, as anyone has experienced with two parallel mirrors, if you put your hand or your body in front of it, you get a sequence of reflections back and forth and back and forth. And I admit I did often stand there and just really take in this weird sensation of other realities that these reflected images might actually be engaging with. It was a total fantasy world, but yes, it does align in some vague sense with what we are thinking about today.
And it goes a long way to explaining your choice of careers. You're not like the rest
those mirrors,
of us. So what is the or a multiverse?
There isn't one idea of what a multiverse might be. There, in fact, in the book, I discuss 9 different variations on the theme of multiverses. One that perhaps is the most straightforward to think about, that I think gives you an anchor when thinking about how our universe might be one of many, is simply this. We all know of the Big Bang, which is this idea that our universe began really small and then underwent this expansion. And as it expanded, it cooled, allowing stars and galaxies to form, the kinds of things you see when you look up in a nice dark night sky. Well, there's a little secret about the Big Bang that perhaps we haven't emphasized enough, which is this. The Big Bang doesn't tell us what happened at time zero itself. It leaves that out. In essence, it leaves out the bang. And we have been trying now for a long time to fill in this missing piece, to really understand how it is that the universe started swelling in the first place. And as we have filled in some of the mathematical details, the math seems to be telling us that the Big Bang may not have been a one-time event. It may not have been unique. There may have been many Big Bangs in the past and still happening today and into the future, each giving rise to its own expanding universe, our universe being the aftermath of simply one of those Big Bangs. And it's in that sense we could be one of many universes.
And is there any limit then to the potential number of universes?
No, it really could grow infinitely big if you allow these processes to unfold as the mathematics suggests that they would. So it does give rise to a picture that's very, very different from what you normally would have thought of when you hear the word universe. We used to think that's everything, the totality. But now it's as if our universe is a single grain of sand in a big beach that has all these other grains of sand, which are other universes.
Well, where would they be? Are they beside us? Are they inside us? Do they surround us? Where are they?
The simplest way to think about it is that they are, roughly speaking, beside us, in the sense that if you took a bird's eye perspective, whatever that would mean, and could see all of these universes laid out in front of you, you would indeed see universe after universe after universe situated side by side. The math shows that the universes would be rapidly separating from each other. They would be moving apart, in fact, near or beyond the speed of light. Each of them would also be expanding. So perhaps another way of thinking about it is, imagine you've got a big cosmic bubble bath with all of these bubbles that are expanding, But our universe is but one of those bubbles, and this big cosmic bubble bath is the new totality, the multiverse that this approach would give you.
So what are the different kinds of multiverse scenarios that scientists are thinking about?
Another that is, again, I think fairly straightforward to grasp relies upon one idea, which is, does space go on infinitely far? So if you were to go into a rocket ship and head out into space, would you keep on going? Would you hit a brick wall at some point, which is like the end of the universe? Or would it be more like the surface of the Earth, where if you head out in one direction and you go far enough, you circle back to your starting point? These are the three main possibilities, but many of us do suspect that space may go on infinitely far. And if it does, there is a startling conclusion that you can draw, which is this. In any finite region of space, matter can only arrange itself in finitely many different ways. It's sort of like the analogy I'm fond of is a deck of cards. If you shuffle a deck of cards, the cards come out in different orders, but there are only finitely many different orders to the cards. So if you shuffle that deck enough times, infinitely many times, the order of the cards has to repeat. Similarly, in an infinite universe, the configuration of the particles have to repeat too, which means that what we experience is happening out there over and over again.
Because we're particles. Does that mean we're happening out there too?
You are particles, I'm particles, everyone who's listening, we are just a configuration of particles. So if this arrangement of particles repeats, then this reality repeats out there over and over again.
Is there a parallel universe where I'm explaining this to you?
I'm sure that there is, and you're probably doing a better job. And
or maybe I'm the evil Spock.
Well, that's the thing. I mean, the evil Spock idea, of course, it's coming from science fiction, but it is exploring, in some sense, a variation on this theme that there are realities out there that either are identical to ours or differ from ours in small ways because the particles are almost replicating the configuration we have here, but not quite. So there are small differences.
This is in line with your work on string theory.
Yes. I have been working on string theory, this approach to a unified theory, for a long time, and I would say that developments in string theory have really fueled the scientific fascination with this possibility of parallel universes. Work in the last few years in string theory has generated a few of its own versions of multiverse proposals.
So this is not thought experiments. This is these are possibilities that scientists are working on. They're working on the equations.
Well, I would actually say that is, in some sense, what we mean by thought experiments. When we talk about thought experiments, it's not just vague thinkings in the back of your mind. We really put mathematical equations behind this thinking. So it is the case that this is a subject that is at the moment divorced from observation, divorced from experiment, which means that we do not know if these ideas are correct. And I need to underscore that because you can't believe in anything until it has observational support or experimental evidence. But what we have found from hundreds of years of investigation is that mathematics has proven to be a powerful guide into realms of reality that at the given moment where the analysis is taking place are beyond what we can see or test or observe.
Remind us of some examples.
There are great examples. So Einstein is perhaps the most famous. Einstein came up with new equations for how the force of gravity works, his so-called general theory of relativity. This is in about 1915. The analysis of those equations showed that the universe should be expanding. That was a shocking idea in 1915, 1916. So shocking that Einstein said, I don't trust the math here. I don't believe the math. And in fact, he tried to fiddle with the math to avoid this conclusion that the universe was expanding. 12 years later, Edwin Hubble, using a powerful telescope, looks out into the cosmos, sees the distant galaxies are rushing apart, and concludes the universe is expanding. The math was right. Einstein's general relativity also predicted black holes, something else that Einstein didn't take seriously. We now, through observations into deep space, know that there are black holes dotting the heavens of the cosmos. So here we see time and again, math is telling us things about the universe that we didn't know to be true at the moment, but ultimately observation confirms. We're following the same tradition. We're seeing where our math takes us. Math that starts with equations that were developed to describe things that we can see. We're following the trail that these mathematical ideas have blazed and continuing onward and seeing where the math takes us.
Were you ever skeptical?
I'm totally skeptical. So if you ask me, do I believe that there are other universes out there? Absolutely not. Again, I don't believe anything until it has observational or experimental evidence. However, when I look at the mathematical ideas that lead us to consider the possibility that there are other universes, I find them very compelling. Compelling enough that I'm willing to invest effort, and many other physicists are willing to invest effort to see, can we extract some experimental consequences that can be tested? Can we extract observational consequences that we may look up with powerful telescopes and be able to confirm?
So are you doing research into parallel universes now?
Yes. What I'm working on right now is within string theory, and I've been doing calculations with a number of students and postdocs at Columbia on trying to see how a universe within the context of a multiverse would evolve, and finding strange things like the so-called extra dimensions that string theory requires can undergo various interesting transmutations, giving rise to universes inside of universes, not just a single bubble in a big bubble bath that we were talking about, but bubbles inside of bubbles.
Give me some more examples of this.
Well, quantum mechanics itself gave us the first multiverse proposal way back in the 1950s. The new idea of quantum mechanics is that the best you can ever do in any circumstance is predict the probability of getting one or another outcome in an experiment. That's not what Newton would have said. Isaac Newton would have said, tell me how things are now, I will use my equations, and I will tell you how they will be tomorrow or the next day. That's, to him, how physics worked. Quantum theory came along and said that actually is an approximation. The true nature of how physics works is probabilistic. Now, here's the weird thing about this probabilistic approach. Let's say the quantum laws say there's a 50% chance that an electron can be here, a 50% chance that it can be over there. Now, indeed, when you do the experiment over and over and over again, half the time you do find it on the left and half on the right, just as the quantum predictions say. So these ideas are confirmed. But still, even today, nearly 100 years, we do not know how to go from the fuzzy probabilistic description that quantum theory gives us to the definite reality that we all see in the world around us. We don't see a world that appears probabilistic. I don't seem to be sitting in one chair or another. As you're looking at me, I seem to be in one definite location. How do we go from the probabilities of the quantum description to the reality that's definite that we all see in the world around us? We don't know. But a guy named Hugh Everett in the 1950s gave a very wild suggestion. He said, if the math is saying that there's a 50% chance that the electron's here and a 50% that it's over there, he said, if you follow the math closely enough, you should conclude that the electron is there and over there, just in two separate universes. And in each universe, you see one or the other outcome. And in each universe, you think there's a definite, unique reality that you are experiencing. But from a bird's eye view, we realize that that's not true. There are two of you, each experiencing one or the other outcome, two parallel universes. The quantum version of this is saying that every possible outcome that's consistent with the laws of physics will be realized in one or another universe. You know, when I phrase this in terms of electrons, it may just sort of tickle the brain, but not really feel like it's relevant to daily life. But every thought you have ever had, every action you've ever undertaken, anything you've ever said amounts to particles going this way or that. If quantum theory says particles will execute all of those outcomes, that means that every decision you've ever made, every possibility that you've ever made a decision about, the other possibilities are realized in other universes. If you said yes in one, you said no in another.
And even the theory that we are actually in a computer, that historians from another time are looking back at us.
Yes.
And we are simulated.
That's another weird one. I consider that a little bit less convincing, this so-called simulated multiverse, compared to the other ones that we've discussed so far. The other multiverses that we've been talking about really emerge from the math of physics. We don't know if they're right. We don't know if this quantum multiverse is right. There are other approaches to trying to make sense of the quantum probabilities. None of these approaches have yet really solidified themselves as the answer. So we consider this multiverse one seriously. The simulated multiverse, though, comes out of more straightforward reasoning, much like what was behind the Matrix.
Okay.
You know, in the Matrix, you've got beings whose brains are being stimulated to think that they are in a given reality, even though they're not. They're just in some pod with their brain plugged into some computer. Could that be the case? The reason I discuss this idea in the book is not because I really take it seriously, but there is an interesting conclusion that this kind of thinking allows you to get to, which is this. For decades, centuries really, people have asked themselves, is mathematics a description of reality, or is mathematics reality itself? Is math something that is invented, or is it discovered? Is math truly out there, woven into the very tapestry of reality? Now, this simulated multiverse gives you a way of thinking about that, because if you and I are right now in a computer simulation, this is pretty good. It feels real to me, right? This definitely is a good masquerade for the reality that we have long thought to be out there, not in a computer simulation. But if this is a computer simulation, imagine opening up that computer. What's going on inside? It's just a lot of ones and zeros being manipulated by mathematical equations. So if this is a computer simulation, just take that on board for a second, we would be mathematics. We would be what mathematics feels. Reality would simply be the unfolding of mathematical equations. And that's the sense in which at least it's possible that math can be more than just a mere description. Math could be reality.
It's fascinating.
Yeah.
You've also made the point that multiverses are harder to avoid than they are to find.
Well, that's the thing. It's not as though we physicists are just hanging out in our offices saying, what new crazy idea can we throw out to see whether or not it catches on, catches fire? It's not that at all. We are doing what physicists through the ages have always done. Looking at data, looking at observations, looking at our best available theories, and doing mathematical analysis and seeing where it takes us. And if you follow relativity far enough, thinking about, say, Einstein and cosmology, you come to this multiple Big Bang idea. Follow the math of quantum mechanics far enough, and you come to these multiple realities where every outcome is realized. Time and time again, the math is coming to some version of our universe being one of many. Again, it doesn't mean it's right, but the important thing to bear in mind is these ideas are really coming to us from the equations. We're not imposing them from an overworked imagination.
Are there any ways of proving this? I'm thinking about the Large Hadron Collider in Switzerland, right?
Yes.
It's up and running. Are there experiments that can be done with that would feed into the work you're doing?
It's conceivable. So one of the multiverse proposals that we haven't yet described is called the brain multiverse. And that's the idea that our universe might be sort of like a giant slice of bread in a big cosmic loaf, with other slices being other universes. It's an idea that comes right out from the mathematics of string theory, and it is potentially testable in Geneva. In Geneva, protons are slammed against each other at fantastically high speed. Now, in the collision, debris is created, and if the collision's hard enough, some of that debris can be ejected off of our brain, off of our slice of bread. How would we know that? Well, if some debris jumps off of our universe, it'll take away some energy, which means there'll be a little energy after the collision compared to how much there was before. A little energy will be missing. So we are looking for these missing energy signatures, and if the data confirms that that energy is missing and there's no other explanation, this could be evidence that our universe is one of many in this so-called brain multiverse.
And that's BRANE.
Yes, I should say it's BRANE. It comes from the word membrane, which is one of the ideas that string theory has come upon in its analysis in the last few years, that strings, which was the ingredient that put string theory on the map, that's why it's called string theory, are not the only ingredients in this approach to unifying nature's laws. There are also extended objects that look like membranes, that's the two-dimensional version, or we call them three brains, which is a three-dimensional version of a membrane and so forth. And yes, this brain idea, BRANE, is that we are living on one of these giant entities that emerge from the math of string theory. It could be that string theory is flat out wrong, and therefore none of this will happen. It could also be that string theory is right, but the collider doesn't have enough energy in those collisions to actually eject some of that debris. So that's the problem.
Do you have to get in line and say, could you do this at the collider for me? Like, how does that work?
In some sense, yes. They just do the experiments, and then it's up to people who analyze the data to try to pull out from the data anything that would support one or another collection of ideas. But it is a strange life. You know, I've been working on string theory for 30 years, something like that. I don't know if it's right. I don't know if it's wrong. I would like to know. In fact, if it's wrong, I would be thrilled. Some people say, what do you mean you'd be thrilled? I'd be thrilled because I'm not wedded to one particular approach to describing the world. I'm wedded to trying to make progress toward truth. And if we can prove that some of the ideas that we've been working on for decades are wrong, I would be thrilled, because then I could turn my attention in a direction that might have a better chance toward reaching truth. So far, however, these ideas are holding together, and our hope is that at the Large Hadron Collider there may be some evidence that we are heading in the right direction.
You know, John Horgan just wrote an article in Scientific American in which he argued that researching multiple universes is immoral. And I'm going to quote here. I'm sure you've read it. First, at a time when we desperately need science to help solve our problems, it's irresponsible for scientists as prominent as Greene to show such a blithe disregard for basic standards of evidence. Second, like religious visions of paradise, multiverses represent an escapist distraction from our world. What do you think of that?
Well, I think it's silly. You know, what we are doing is pushing the boundaries of science in the traditional way. And when you're pushing the boundary, of course you're moving into territory that has not yet received experimental or observational support. But as I hope is clear in our discussion so far, that is paramount. So it's not that we're disregarding or saying you no longer need observational or experimental evidence. No. We're saying here are a collection of fascinating ideas that are emerging from the cutting-edge analysis, and we hope that we'll be able to either prove them right or wrong in the not-too-distant future. You know, scientists perform a lot of research trying to deal with critical problems in the world around us. And scientists whose internal compass pushes them more in that direction, that is fantastic. I'm a scientist, and many of my colleagues are scientists whose compass pushes them more into the theoretical ideas, trying to answer questions that we've asked for thousands of years. How did the universe begin? Where did this cosmos come from? What is the true nature of reality? These questions are deep and important, and we as a species have asked them for thousands of years, and we're carrying on that tradition.
As you know, it can be a difficult struggle to get people to buy into well-established mainstream science in the U.S. right now, like the science of evolution, the science of climate change. Is this the right kind of social or political environment to be trying to do this kind of work?
It is a challenge, but what I have found is that much of the resistance to science is coming from the way that we teach it and the way that we present it. Many people are intimidated by the ideas of science. Science is presented in a way where they feel like they don't get it. They feel like they're not smart enough to get it, and that's a failure of how we present it. So, you know, I've spoken to kids for whom science was memorize this, go into the class, take a test, and just spit it out and do your best to regurgitate these facts and figures that you learned in a book. That's not science. And when I start to talk to these kids and really tell them about the nature of black holes in space and the possibility of our universe starting with a Big Bang and what things might be like 100 billion years from now, I watch as their eyes open up. And so often I'm in the company of these kids and they say, "That's science?" I was like, yes, that is science. And that is what is missing. We need to have a focus on the big ideas, not just on the details that can be tested. And a focus on the big ideas will make the kids more excited to learn the details, because now they understand why it is that those details are important. They're not important in their own right. They're important for what they tell us about the world, about the universe. And that's what we need to do.
Brian Greene, thank you for coming in.
My pleasure. Thank you.
Brian Greene's new book is The Hidden Reality, Parallel Universes and the Deep Laws of the Cosmos, available in a universe near you. He was in our Toronto studio.